Solar flares, intense bursts of radiation emanating from the sun's atmosphere, have profound implications for both Earth's climate and the endeavors of space exploration. These powerful phenomena, driven by the sun's magnetic activity, influence various terrestrial and extraterrestrial environments. Understanding their effects is crucial for mitigating risks and leveraging opportunities in our increasingly space-dependent world. While solar flares primarily affect the upper atmosphere, their influence on Earth's climate is indirect but noteworthy. Solar flares emit vast amounts of electromagnetic radiation, including X-rays and ultraviolet light, which can temporarily alter the ionosphere. This layer of the atmosphere is crucial for radio communication and navigation systems. When a solar flare occurs, the increased ionization can disrupt these systems, leading to temporary communication blackouts and navigation errors. The energy from solar flares can also interact with the Earth's magnetosphere, causing geomagnetic storms. These storms enhance the auroras and can induce electrical currents and power lines, potentially causing power grid failures. However, the direct influence of solar flares on the lower atmosphere and climate systems, such as temperature and weather patterns, remains a subject of ongoing research. Some studies suggest that prolonged periods of high solar activity, including frequent solar flares, could correlate with slight changes in global temperatures due to increased solar radiation. Nevertheless, the effect is relatively minor compared to other climatic drivers like greenhouse gas concentrations. The impact of solar flares on space exploration is significant and multifaceted. Astronauts and spacecraft outside Earth's protective atmosphere and magnetosphere are particularly vulnerable to the intense radiation from solar flares. High doses of this radiation can pose serious health risks to astronauts, including increased cancer risk and acute radiation sickness. This necessitates the development of advanced shielding technologies and comprehensive monitoring systems to protect human spacefarers. Solar flares also affect the functionality and safety of spacecraft. The radiation can damage onboard electronics, degrade solar panels, and interfere with satellite communications. For instance, during intense solar flare events, satellite operators often switch off sensitive instruments and reorient spacecraft to minimize exposure. This precautionary approach underscores the need for robust design and materials capable of withstanding solar radiation. Moreover, solar flares can accelerate particles to nearly the speed of light, creating solar energetic particle-SAPE events. These particles can penetrate spacecraft and pose a threat to both astronauts and onboard systems. Missions to the Moon, Mars, and beyond must incorporate strategies to predict, monitor, and mitigate the effects of these events to ensure mission success and crew safety. Given the substantial impact of solar flares, effective mitigation strategies are essential. Advances in space weather forecasting are crucial for providing early warnings of solar flare activity. This involves monitoring the sun using a variety of space-based and ground-based observatories, which can detect signs of impending flares and alert affected sectors. In space exploration, enhanced spacecraft design incorporating radiation-hardened components and improved shielding materials can reduce vulnerability to solar flare-induced damage. Additionally, mission planning can include contingencies for solar flare events, such as safe zones within spacecraft where astronauts can seek shelter during high radiation periods. Continued research is vital to better understand the complex interactions between solar flares, the Earth's climate, and space environments. Multidisciplinary studies combining solar physics, atmospheric science, and space engineering will yield insights that can inform both climate models and the design of future space missions. Solar flares, while a natural part of the sun's activity, present significant challenges and opportunities for Earth and space exploration. Their influence on Earth's climate, though subtle, underscores the interconnectedness of our planetary systems. In space, the risks posed by solar flares necessitate robust protective measures to safeguard both human and technological assets. As our reliance on space-based infrastructure grows and human exploration extends further into the cosmos, understanding and mitigating the effects of solar flares will be essential for ensuring the safety and success of these ventures. We have a question for you. How can we best prepare for the challenges posed by solar flares to protect our planet and advance space exploration? Let us know in the comments.